Hi, I'm Goran. Today I am talking about our experience of using diff-based mutation testing at Google for the past 6 years. Now, before we dive into any details, let's first take a look at what the general day-to-day workflow of a developer looks like. The developer first prepares a diff, which they send for code review, at which point various static and dynamic analyses will be executed and their findings reported back to the author. Human reviewers can also post comments on the code. Only when both our organic friends and our silicon overlords are happy with the state of the code can it be merged back into the version control system. Given this workflow, it makes sense to provide concrete test goals to the developers at this point in the middle during the analysis. So let's take a look at a few of these test goals. Given some source code in the diff, one of the simplest things we can surface is code coverage. Lines that are covered by tests and lines that are not covered by tests. And these uncovered lines present very simple test goals. The developer can go look at them and then add missing test cases to fulfill these test goals. Now, let's look at another type, a more complex type of test goals, namely mutants. Mutation testing is a systematic injection of faults into the program with the goal of evaluating the test suite's capabilities in detecting those faults. For example, in the first line here, we could change the if condition to be if false, yielding a mutant, and we can change the x plus 1 to x minus 1, producing another mutant. And finally, we can replace return sum to return null, yielding yet another mutant. Given that no test cases fail for these changes, the developer can now use these mutants as test goals. They can go and for each of the mutants, they can add test cases that would fail when the code is edited in such a way, and thus fulfilling the test goals. Okay, let's zoom in on this developer workflow a little bit to understand the life of a diff at Google a little bit better. The developer first prepares a diff, and they send it for review, at which point some quick checks can be immediately executed and reported back, for example, formatting errors or linter errors. The developer is then expected to take into account those errors and then improve their code in a way that the errors will be eliminated. At that point, another set of checks can be executed, for example, mutation testing or code coverage. And testing goals can be reported to the developer, like uncovered lines or live mutants. We expect the developer to take some of these into account as well, and they can edit their code to add missing test cases for some of the test goals. At which point, some human reviewers might post some higher level findings about the code and get the developer to produce yet another version of their code. And finally, if everyone is happy with this state, this code can now be submitted back into the version control system. Given this process, we can ask ourselves whether reporting mutants as test goals changes anything regarding testing quality and quantity. As I briefly mentioned earlier, we have been using mutation testing for 6 years, so armed with the experience and the data we have, we can answer the following specific questions. Do developers write more tests based on mutants? Namely, do they use the mutants as test goals? Are those tests of good quality? And finally, are those mutants that we present as test goals representative of real bugs? Because if they're not, there's no sense in writing test cases for them. To answer our questions, we have constructed two datasets, one with mutants and coverage, and the other with only coverage surfaced. The mutant dataset contained 15 million mutants, and the coverage dataset contained 9 million diffs with coverage surfaced in them. If you look at the code review flow, at the beginning, when the developer prepares a diff, there is some amount of testing in the diff present. Most of the code in Google is well tested, and there's always, it would be very strange if the diffs did not contain tests. So at the beginning, we do expect to see some tests there. Then there comes the point of intervention, where we can report findings like live mutants or uncovered lines. If the developers use those as test goals, we would expect to see an increase of the testing that happens in the diff just before submission. And we can call that newly added test cases delta test. If you look at our two datasets, the number of tests added during code review in the mutation testing dataset is significantly higher than that of coverage. For coverage, the number of tests added is stable for the same file modified over time. As file gets mutated, however, it gets more and more added tests. We expect this to plateau at some point, and that is a question for future research. The main point here is that mutants as test goals elicit a substantially larger number of tests than coverage. But what are the effects on testing quality? How does continuous mutation testing affect the survivability of the mutants on a project? Let's look at the code review process again. At the beginning, when the diff is sent for review, there is some amount of live mutants in the code. Then comes the point of intervention, where we can report live mutants, those that exist. And finally, if developers use these live mutants as test goals, we would expect to see less live mutants when the code is submitted, because there were extra test cases written for them and they are thus killed. We can call this delta mutants. And indeed, we see that during the review, there are significantly more live mutants in the code than there is at the submission time, meaning that the tests that the developers write based on this intervention actually kill those mutants. Let's talk about fault coupling. Source code can have bugs anywhere around it, and we can generate mutants in different areas of the code as well. The important question is, do these mutants and bugs coincide? More specifically, the coupling hypothesis states that the tests sensitive enough to detect simple mutants are also sensitive enough to detect more complex real faults. In order to test this, we've constructed an experiment. We mined our version control systems for explicit bug fixes, and then we ended up with a bunch of buggy code on one side and fixed code on the other side, with an explicit fixing diff. The experiment, of course, in the buggy source code, we have a bug in some place that does not exist in the fixed source code, and hopefully the fixed source code also has an extra test case written to detect this bug. So what we did for the experiment is we generated all the mutants in both the buggy source code and the fixed source code. Now, we executed all the tests in both sides of the experiment, and here we marked the mutants that were killed by the test. The next step is to detect whether there is some kind of coupling between the mutants and the bug. And that means that there has to be some mutants that are live in the buggy source code around the bug, that are dead, that are killed in the fixed source code by the newly added test case. And indeed, we call these mutants coupled to this fault. In our experiment, we analyzed more than 1,500 bugs, generated more than 400,000 mutants, and executed 33 million test suites to evaluate this. And indeed, we found around 70% coupling, meaning that in 70% of cases when there was a bug, there was a live mutant that coupled to the bug in the same area of the code, which, had we reported to the developers, might have prevented this bug from happening in the first place. To conclude, mutants reported during code review make for actionable test calls. The developers use them to implement missing test cases with which they kill those mutants. And because these mutants are coupled to a fault, we can say that diff-based mutation testing improves testing practices. You can read more about our research in the papers named below. Thank you very much.
So, hello everyone. What a fantastic paper and great work from Google. I really must thank all the authors and especially Goran here. A very nice video as well. And I'm lucky enough to have you again after we met in ICSE on the previous paper. So my first question is, of course, how much is this used across Google? Is it sort of a mandatory in your process for everyone, or is it just a team in some place?
Thank you, Sigrid. It's nice to be with you again. Thanks for sharing. Well, mutation testing has always been opt-in in Google, but we have more or less everyone opted in by now. In the last year, we have been ramping it up more officially, let's say, but more or less anyone working on the internal code that is not open source like Chrome or Android is probably using mutation testing in every diff they submit.
Yeah, this is really, I think, the best in the industry. I must say, I'm very impressed. We also have good questions here in the chat. Please write your questions. You have the chance now. So first, Michael here says, cool work. Did you measure whatever the test added after the mutation report did later on reveal bugs that would not have been found by other tests?
So we know for sure that at the time they did not find the bug, and they would have had they been written. But later on, they might be catching new bugs for all we know, but we have not measured that.
Okay. So could it, and also Stefan had, could there be other stronger mutants that you think would increase the coupling even more?
Probably, but because we only generate one mutant in a line, and this full coupling was we specially changed our production system to generate all mutants as standard permutation testing, just to verify this hypothesis. That cost a huge amount of resources, and we had to do it over months during weekends when there is no load on our testing infrastructure, and that's why we only have the data for this set. And for us, it's infeasible to be able to run that on every diff to generate all mutants. Basically, we will not be able to scale to 1% of our needs, and especially taking into account the shared destiny of the mutants. That if you generate 20 of them, most of them will either fail or pass. So we only generate the one. So while there might be other stronger mutants that would increase the coupling, we are fine with trading that probability with the fact that we couldn't even run the system if we generated others. And of course, we do use some kind of a machine learning ASD distance metric to be able to pick the best mutant operator type for the given mutation in question based on the ASD of the point of mutation. So we don't pick them at random anymore. And we hope that those mutants are stronger because they have a higher probability first to survive and then to get the positive feedback by a developer clicking please fix on the actual mutant, or the reviewer, actually, not the developer. So that's a strong indication that this mutant is of a higher quality. So we do try to pick the higher quality ones, but that's the extent of the work that we have done.
Yeah, so we discussed it maybe a bit earlier. You have done how you pick these mutants. So you really have written another paper. You spend most of your work there, you say, picking the right mutants, and you have done an extension on that, describing the heuristics of doing that, right?
Yes. We have a preprint with an extension of heuristics where we name, it's 10 pages of heuristics that we do to try to not generate mutants that are not useful. We call them productive or not productive. And basically 95% of the work that we've been doing is in that area. Because running the mutants, generating them, parsing ASDs, it's all very tedious and costly, but it's not really complicated per se. The hardest part is to only find the mutants that the developers would find useful to fix. Because we can't enforce this. People will only fix mutants if they think, when they see them, this is something I should do, this is useful for me. We don't have any levers to make them do anything. The only thing they could do is turn off mutation testing for their project if they start seeing mutants that they don't find useful. So that's why the hardest part was just actually filtering out the huge majority of mutants that would not be fixed by the developer.
So this is Ashkan here have asked, so how did you decide on the number of mutants that you would like to use in the first place? And I guess that's the heuristics you applied, and then you reduce the set, and then.
Yeah, so I first started with reading the literature and implementing it as it should be, we generate all the mutants of all the types in every line, and I was running it for myself, and I found that I generated only for the actual mutagenesis code itself, I generated the amount of mutants that I wouldn't be able to go through in a month, just for my own code, which was very small at the time. I went through like 20, and I realized 19 of them were useless and hard to interpret. So I just I basically did not do anything on the project for a few months, just trying to think about how to go about this. And it was very costly to evaluate all the tests, because we have a single repository where if you link something in, then there's many things testing it. So to be able to actually evaluate it properly, you need to run thousands of tests in some cases, depending on the dependency layering. So I was not, basically I was forced to only choose one, because if I wanted to do more, this project would have died in the beginning, because first, I wouldn't have resources to run it, and then second, I myself would not be able to force myself to go through them, because there were so many.
Yeah. Okay, so this is, I think, what you're saying is what stops a lot of industries going, because they get overwhelmed and then they like, oh, this is too difficult. So do you have any advice for other industries how to sort of fix that starting point? Let's put it like that.
Yeah, definitely. So I think the heuristics are critical, and I think anyone who reads our extension that is like 10 pages of heuristics, they will also get a feeling about what types of things should be suppressed and what types not. So they can easily go in their company and find equivalent set of stuff to suppress, and then they can go from there. And definitely the mutants that we use are basically test goals, and we try to get developers to write tests for something that they think is actually useful. We don't really care that they kill all of them, because if they decide it shouldn't be killed, I want them not to kill them, because it would be a waste of time. So there's no like optimizing a certain metric. We don't measure any metrics, mutation score or anything. We just measure the quality of the mutants, where people click please fix. We like that.
You don't force people.
No, there's no. I mean, it would be maybe an interesting thing to try out, but it's just not possible in the way we work. So you need to actually convince people that this is useful for their project, and they need to want to do it. And the only thing we measure is the ratio of please fix and not useful feedback that we get on the mutants, and we try to keep the not useful very low. But of course, it's around 10%. 15% depending on the week, because there's equivalent mutants everywhere. There's a lot of stuff that we haven't suppressed yet, and probably will never be able to do. But people are generally very happy with the mutants, so I think we can live with the 10 to 15%.
That's really valuable information. Thank you, Goran. So, are there any other questions in the chat? We still have 1 minute to go. Well, I must say I'm hugely impressed by this work. I think it's also very good you keep it on a voluntary basis and instead trying to adapt the tool. So here we got one, Michael. Can you characterize the useful mutants, and do they resemble realistic bugs?
So I wouldn't say yes or no. There are some that do resemble realistic bugs, but there are many that don't. Like if you delete like 10 lines of code, probably the developer is not going to not remember to write 10 lines of code. So that's not a realistic bug. But it basically points, and that's why one is enough. It points to an area that is weakly tested, that I have also learned to predict where I will get mutants when I write my tests. So I rarely see them, because I know my test is bad, and I immediately add, even before running anything, I add the stuff there, because I learned to anticipate the mutant. So basically we use them as points to a code that is not ideally tested, and they don't have to be similar to bugs.
Okay, there are more questions. I'm sorry we